polynomial in the 17th century. The Pascal triangle consists in placing 1 in all the sides, and in the middle, for the numbers in the middle, we're going to fill with the sum or the addition of the number in the upper left and in the upper right. The Pascal's triangle will give us the coefficients of the expansion of a binomial to a degree. For example, here, a plus b elevated to the second degree is equal to a to the 2 plus 2 times ab plus b to the 2. The coefficients of the terms are 1, 2, and 1. And if we locate in the Pascal's triangle, in the third line that corresponds to the exponent 2, the coefficients are going to be 1, 2, and 1.
Now, to know the exponents of the expansion of the binomial to a certain degree, we will use the binomial theorem. This is our formula that we'll use, and it means that for any positive integer n, the power of the sum of numbers a and b can be expressed as the sum of n plus 1 terms of the following problem. This is the problems or the exercises we have to resolve. First, we were told to use the binomial theorem to expand this expression. Then, we're told to find the last two terms in the expansion of this other expression, and to find the 24th term in this binomial.
We're going to do the following procedure. To find the coefficients, we're going to use the formula n factorial divided by k factorial multiplied by n minus k factorial. Remember that k is the position of the term minus 1. For example, the first term minus 1 is equal to 0. So with the value of k is going to be 0. Well, now we're going to deal with the first, so it's going to be 0, and the coefficient is going to be 1. And then we continue with the second position, that's going to be the k equal 1. Then with all the other positions, we're going to apply the same formula. And finally, with all this process, we can get that the coefficients of the expansion of this binomial is going to be 1, 7, 21, 35, 35, 21, 7, and 1.
Now we'll have to find the exponents. For the first term, we'll do the following. In the first variable, the exponent will be equal to the first exponent of the whole binomial minus the position. So the first term will be equal to the position 0, so the exponent will remain being 7. To the next variable, which is y, the exponent will be equal to the position in which it is. So if it's in the first position, it will be 0. So there will be no exponent, and the first term will be x to the 7. Now when doing the next terms, we have to remember that if it's a difference between two terms, the value k, if the value k is not number, it will give us a negative coefficient. And if the value k is an even number, it will give us a positive coefficient. We will do the same procedure for the following terms, and we will add also the coefficient.
And we expand our expression. Is that we have to find the last three terms of the expression a to the 2/3 plus b, all of these elevated to 20. Well, first we're going to find the coefficients, and we're going to apply the same formula we did in the last exercise. So we're going to substitute with this formula with the values of 20 as n and 20 as n, and also as. So we're going to have the coefficient 1 And if we repeat the following procedure with the other term, after all this process, we're going to find out that the last three coefficients will be 1, 20, and 190.
Now, to find the exponents, we apply the same formulas with the past exercise. But in this case, considering that A is already elevated to a power, we have to multiply it in order to know the real exponent of A. Like in this case, we have the A is elevated to 2/3, so we'll have to multiply 2/3 times 2, that will give us 4/3. So after multiplying these two exponents, we will get that the last three terms of the expression will be the following.
The 24th term in the expansion of this binomial, that is x minus 2, all of these elevated to 25. So first we're going to find the coefficients. And we're going to use the same formula we used in the last exercises, considering that n is going to be 25 and that k is going to be 23, because remember, it's the 24th term, that's the position, minus 1. So it's going to be 23. Well, now, we substitute the formula with the values 25 as n and 23 as k. And after this process, we're going to find that the coefficient
To
is
know the exponents, we will use the formula that we've been using through all the exercises. This pretty formula. And we will substitute, remembering that n will be 25 and k will be 23. We'll have to remember that since we are elevating a negative number and is an odd exponent, we will get a negative coefficient as we get in here. And well, okay, so we multiply this negative coefficient by all this, and we will get in the 24th term in the expansion.
After all of these procedures, we can get to our conclusion. In the first exercise, we had to expand the expression x plus 2 times y, all of these elevated to the 7th degree. And our answer of this expansion is going to be x to the 7th degree minus 14 times x to the 6th degree times y plus 84 times x to the 5th degree times y squared minus 280 times x to the 4th degree times y cubic plus 560 times x to the cube times y to the 4th degree minus 672 times x squared times y to the 5th degree plus 448 times x times y to the 6th degree minus 128 times y to the 7th degree.
In the second exercise, we have to find out the last two terms of a to the 2/3 degree plus b, all of these elevated to the 20th degree. So we will find out that the last two terms will be a to the 4/3 degree, b elevated to the 18 plus 20 times a to the 2/3 times b to the 19 plus 190 times b to the 18.
Finally, our last exercise, we are going to find out that the 24th term of x plus 2, all of these to the 25th degree, the 44th term of this expansion is going to be minus 2,560,582,400 times x squared